Okay, so today we are going to deal with weak acids and weak bases, okay? So when you have a strong acid or strong base question, they completely dissociate or the reaction is 100% in the forward direction, which means then you can use Stoic to calculate H or OH concentration depending if you have an acid or a base. And so these questions will be out of very few marks because it's very easy to do. When you have a weak acid or weak base, they do not completely dissociate and equilibrium is established. So when equilibrium is established, then of course we have to do ice. So as we go through, basically, we have to do 3 more examples, I think. And so each time you're going to see, based on the given information, the items you can calculate. So again, there is a lot we can do with very little information because of the conjugate pairs and the protonation of water. So another formula is this. You can even convert between Ka and Kb using Kw. Okay, so this is another equation that is found on the reference sheet, as well as the Kw value is 1 times 10 to the negative 14. So again, because of the properties of water, then you can have acidic and basic properties. If you have an acid, a weak acid, the Ka value will be small, but then if you calculate Kb, it's going to be extremely small. And then vice versa, if you have a base, a weak base, and you're given a Kb, then the Ka will be extremely small. So similar to when we used Kw equals hydrogen ion concentration times hydroxide to convert between values, one of them is larger and then the other one is smaller. Okay, so the same thing will be true if you use this relationship. Okay, so when you do the ice table for a weak acid or a weak base, then you have to write your own dissociation equation. So when you do the dissociation, technically it's going to be either the acid or the base, which you'll be given the formula of plus water. But because water is a liquid and we're going to cross it out in the ice table, sometimes you'll find it's missing and sometimes it's included because it doesn't really matter. We're going to cross it out anyways. And sometimes chemists are lazy. Okay? So if you have a weak acid, and you should be using, this time when we don't have something strong, then you should use an equilibrium arrow. Whatever version you used in the last unit is fine. So really it's a 50-50 chance. So you have a weak acid or a weak base. So a weak acid, of course, is a donor or gives away a proton. So sometimes, and we're going to do one at a time, one proton at a time. So the coefficients will all be 1, so that's nice. And you can even do this sort of weirdly, I guess. Like one of the exam review questions gives you urine, and it tells you to just write urine and then put urine H+. So the formula itself for the conjugate acid or the conjugate base isn't really you don't really have to stress about that. It's more about what is the other ion that you produce. So if you have a proton donor or an acid, then usually you're going to get something, if you're getting rid of a positive, it's going to be negative or an anion. And yes, that's important. The conjugate is of course important. That's a big part of this unit. But when we do the math, so when we are asked to find pH, then we need to decide, or pOH, what is the other ion that's going to be produced. So if you have an anion, which is negative, then the other one has to be positive. Okay, so you can write hydronium, or if you don't include the water, you can write H+. So whenever you do an acid question, you can find pH as soon as you solve for X. So when you have acids and bases are always aqueous, and that should be given to you in the question. Water's a liquid, so we're going to cross it out anyways. And then, of course, ions are aqueous. So when you have a hydrogen acceptor or a proton acceptor, a base, it's going to become positive. Some people will even write it like this. Okay, with the hydrogen as a positive, it's kind of up to you. That is the ion, the conjugate. And so if the base takes a hydrogen from the water, then remember water's HOH, so what's left over? OH. Okay, so yes, we should write an appropriate conjugate, but really what matters is it going to be hydrogen ions produced or hydronium, or is it going to be hydroxide? And what you'll find is every time, and I've said this before, every time you have a base question, then for the standard is we look at a pH scale, not pOH, so then every base question has an extra step, okay? So the hydrogen or hydronium or the hydroxide ion is really what matters in terms of acid-base equilibrium. Okay, so you need to write your own equation first. And then, so again, when you go to do the ICE questions, first of all, they're going to be out of more marks. But also when you're looking if something is going to be weak, then look for either the Ka or Kb value. When you have a weak acid, it's got that COOH often. So when we do this example, formic acid, COOH, ethanoic acid, COOH, okay? So, and then for a base, if you happen to look at page 803, most of those bases have NH, like they're derivatives of ammonia. Okay, so that's just one way to look at it. The Ka value is a really good way. We talked about the pH being low, but not super low. But again, a good way to, the strong acid, strong base questions would be out of like 2 marks. These questions will be more like an ICE question, 5, 6, 7, many more marks. And you know what? Sometimes it even says, propanoic acid is a weak acid. But I can't guarantee the homework questions. The textbook questions are like that. Okay, so then for the ice table, sort of similar to dissociation for the solid, then we talked about this yesterday. It's like you have the acid or the base and you put it in water. So initially, the concentration of the ions on the product side, both of them, is going to be 0. Okay, so even before solubility, 97% of the questions in the intro equilibrium unit, the product started with 0, right? So it's exactly the same. Then we're still going to use the change to be x. We don't know what it is. We need to find what it is. And then we're going to solve you could solve for x at equilibrium if you were given the k value, or you could use the pH to help us find the concentration of ions. So pH, because that's saying what's the power of the hydrogen ion, then it's like after the solution has dissolved, then that is when the pH can be calculated. So even though, just like with solubility, it didn't necessarily say at equilibrium, pH is used because the initial concentration is 0 of ions, then the pH can be used to calculate hydrogen or hydronium at equilibrium. Okay, so you could be given pH for concentration at equilibrium. I'm just going to switch for 2 seconds. And we talked about that percent ionization could be used for equilibrium. Sorry, what's going on here? Okay, so again, lots of stuff we could do with very little given information. So once you write the dissociation equation and build your ice table, use the formula sheet to help you solve your problem. Okay, so a 0.1 molar solution of formic acid. So right away it says acid right there. It's got the COOH. You're given a pH that's low but not super low, and you're asked to find a Ka value. So any of those things can tell you that this is a weak substance. And again, I'm not here to trick you, so I wouldn't ask you to calculate a Ka value for something strong because it would be very large. What's the point? Okay, so this means that you have to do ice. And again, I'll give you what this is, the acid or the base. but you have to write your own dissociation formula. So if you want to include the water, again, it's up to you. We're going to cross it out. If you include the water, then you're going to get technically H3O plus. If you're not going to include the water, then it would just be H plus, but it actually really doesn't matter. And again, even if the conjugate base to this, I mean, yes, it matters, but it matters more what the other ion is produced. So if you forget that technically the hydrogen connected to the oxygen is the one that's donated, if you got rid of the one on the front, I wouldn't take marks off, okay? That it doesn't really matter. You just need to know if it's an acid, it's going to give away a proton. If it gives away a proton, that means water has to be the acceptor and you get H3O plus. Or you can write H plus, whatever. Okay, so not unlike the solubility problems, once you had the equation, then the ice table itself was pretty straightforward. Do I have a concentration of HCOOH? Yes, it's 0.1. I don't include the water, so I get to cross it out. We said the ion concentration is going to be 0. We don't have any ions to start with. And then just like the last unit, you can't go down from 0. So this side, the product side, has to increase or be positive X. Meaning the reactant side goes down. Okay, so every ice table problem will be the same. You'll have two versions. If it's an acid, you'll get H3O plus. If it's a base, you'll get OH. And now it's decision time. Do I know X at equilibrium, or do I know the equilibrium constant? So since we are asked to find the equilibrium constant, that means that we need to solve for X using information we're already given. So we haven't used the pH yet, okay? I know I wrote it over here with lots of stars, but I'm going to write it again. And, you decide how you want to format your note. The pH is going to be used for the H plus or H3O plus concentration, so I'm going to write it over here, but you decide how your note's formatted. Okay, so this formula is on the sheet. The formula sheet, inverse of log. Write your answer in scientific notation or not, that's up to you. I don't care. One annoying thing about this, pH has no units, the K value has no units, but concentration does have units. So that's a very annoying communication mark to lose. And it's unfortunate because there's so many other things in this section that have no units. Okay, so it tells us the H3O plus at equilibrium, that's perfect. It's only X, and it will be like this every time. Every equation you write should have coefficients of 1, which makes your life easier. So when you do these problems, just read the question carefully. Just like last unit, you could have stopped here. I found the equilibrium concentrations. This question wants you to calculate Ka as well. So we reviewed what the K was yesterday, products over reactants, coefficients become exponents, no liquids. Just like the last unit, write out the equilibrium law because you get marks for it, then plug in the values. So you can see that this question, again, would be like 5 or 6 marks compared to strong, which would be like 2. You don't have to do any of this ice work. Often these answers are given as scientific notation, so I'll include it, but again, I don't care. You do you. So we'll do one more acid example where we can't solve for X. We have to use the equilibrium law to solve for X. And then we'll do a base question. But like I said, the majority of questions are acids because weak acids are much more common and much more usable than weak bases. Okay, so a 1 molar solution of CH3, there it is again, the COOH. This time you're actually given a Ka value, and it's obviously a very small number. So that can tell you that it's a weak acid as well, because again, having a K value for strong acid or strong base is not a thing. Okay, so once again, we're going to find the equilibrium concentrations. Even that tells you right there that you're going to do ice. Okay, so there is lots of clues about what kind of solution you have. So so it's virtually identical. Again, we have the acid. Whether you include the water or not, because we're just going to cross it out. Try your very best to get rid of the hydrogen connected to the oxygen. But if you forgot to do that, I wouldn't take marks off. But then if this is an acid, which It tells you the Ka. A stands for acid. That means water's the base or the acceptor. Okay, so this is really the ion that matters much more, the H3O plus. You'll see when we do the base question, again, there's always an extra step for bases because we don't deal with POH. And again, whether you're given X or not, start with the concentration you're given, which is 1. Ions are 0. So every question you can get this far and then keep reading or decide, what do I do now? Okay? So in the last question, we were given the concentration, we were given the acid, but we were given pH. This time, we are not given pH. We're asked to find it, but we are given K, and specifically Ka. So just like in the intro to equilibrium unit, the last one, then you had to, if you were given the K value, you had to solve for X. Okay? And solving for X using the equilibrium law sometimes meant the quadratic formula. And then when we got to the solubility section, we could use an approximation to help us not have to do that. And in the solubility section, the K values were like 8 times 10 to the negative 7, negative 9, negative 13. Those numbers were tiny. So having to figure out whether the 100 rule would work was really sort of a moot point because it always worked because the K values were so small. Technically, in this unit, there are questions in the textbook where I don't think they should use the 100 rule, and they do anyways. So you might as well use the approximation to help you out. Last time, if you forgot and you made a quadratic equation and tried to use the quadratic formula, because the numbers were so small, some calculators might have said error, like it wouldn't have done anything for you. This time, that shouldn't happen. So if you hated the 100 rule and you didn't want to use it, then you could write a quadratic equation that will probably give you 2 roots or 2 x values because these K values aren't quite as small. But I mean, it helps simplify your math, so it's kind of up to you. So when we did the 100 rule, these x values were by themselves. We didn't touch those. We looked at the one that had the number minus x or plus x and decided whether this number was bigger than this number, at least 100 times bigger. So 1 and 10 to the negative 5 this is definitely 2 decimal places bigger. But again, you can certainly try to do the quadratic formula here, but you can also simplify it. What did I write last time? 1.0 is much greater than Ka, something like that. Like I said, your textbook uses the 100 rule when I don't think they should, but so they love it. So might as well, makes our math easier. So instead of having to get an equation in standard form and use the quadratic formula to solve for x, all we have to do is square root. Dividing by 1 does not change the math, or multiplying by 1. And then if you have x times x, that's x squared. You just have to square root. And just like the last unit as well, because we're going to sub in x with nothing else with it, then you can just ignore the negative root because we can't have a negative x value. So using the 100 rule, even though it might seem like magic, it does make your life easier. And in solubility equilibrium, it works for sure. And this one, your textbook just uses it, so why not? Actually, okay, so just like last time, whatever you were choosing to do, if you like therefore statements, therefore the equilibrium concentration is, you could plug it back into your E line. You can use scientific notation or not, just make sure your concentration has units. I'm kind of out of room there, so even you can, when you do this math to do 1 minus the x value, the number you get is 0.99576. So even that, you're like, okay, that's 1, right? So you're kind of proving that the 100 rule is good. But I'll write down all my decimal places. But again, rounding this to 1 sort of makes more sense. Okay, so now we just have to make sure that we've answered all what the question wants us to do. So it asks us for pH. So we have the hydrogen ion concentration, so we can find pH. And again, before you do your math, you can think about the logic of your answer. It should be below 7, but not super low because it's a weak acid. And we get 2.37. So pretty good. So with this information, I could have got you to calculate POH, the OH concentration. We did the one today, Ka times Kb is Kw. I could have asked you to convert Ka into Kb. So just make sure you take a look at what the question's asking and make sure you do all the work. Because once you have the ICE table and you decide whether you have X or not, then the rest of it, you can use that formula sheet to help you. Hello? Can you say that again? Sorry? That's okay. Here again. Okay, and then the last one we're going to do is a base. So because there are less base questions, then sometimes it can be tricky because you haven't practiced the dissociation equation as much. But if you have an acid and you're going to get H3O plus and you're really good at that, then the base has to be not the same, right? So maybe that's your clue. It does say methylamine. And you're lucky, you've already done organic. So you know that amines are weak bases. Again, you can look for the NH. There's no COOH this time. It asks you to find KB first. So maybe that's your clue that it's a base. Base questions are definitely a little bit trickier. So again, even though this methylamine is a weird formula, you want to show that the base is going to be a proton acceptor. So when you write the formula of the cation on the other side, really it's going to be CH3NH2 and another hydrogen. So even if you wrote this, okay, even that's good enough. Just put the hydrogen with it. Technically, not sort of similarly to the COOH, this CH3 is boring. The nitrogen is where it's at. So it's got the extra lone pair that it can the hydrogen, the proton can be attracted to. That's where the hydrogen would be accepted. But the cation or the conjugate acid, the formula for that is, it's important, but it's not going to have a huge impact on your math if you forget what that is, okay? So in the general equation over here, I wrote cation with the H plus, so you can even do that if you would like. Just put CH3NH2 and then the H plus separately. That's okay. The big thing is that this substance is a proton acceptor. Which means that water, which is HOH, is going to be the donor this time. So what's left over? OH. And the OH, just like the H3O plus, is going to have a bigger impact on the math that we do. The acid-base math, pH, POH, whatever. But the equation, once you have the dissociation equation, yes, it's different, but the ice table principles are the same. Given the initial concentration of whatever this weak substance happens to be a base, cross out the water, the ions are 0. And then decide what's what. So this question, we are asked for the equilibrium constant, which means that we need to be able to solve for x. So this time we're given the percent ionization, which we talked about yesterday. So the percent ionization, just like pH, can be used to find a value at equilibrium. So even though it is in the like the initial slides of this note, I'm going to write it again here. So yesterday we said that the percent ionization formula, you could use either ion, and the same thing is true here. Both of them are X. So most people will do the OH, but it really actually doesn't matter. And just like with pH and the inverse of pH, the 10 to the power of negative pH, this is the percent ionization formula is also on the formula sheet. So once you do the ICE table, then use that sheet to help you. Okay, so when you have a percentage, some of your brains will automatically get rid of the percent sign and move it 2 decimal places to the left or divide by 100. You can show all of your work. You can definitely skip steps here. You decide, okay? Okay, so divide by 100. Multiply by 0.1. Even some of you will recognize that that's just one more decimal place. That's fine. You can definitely do shortcuts. And again, you can use either ion in the top of the fraction. You could even sub in the X if that makes more sense to you, whatever. Okay, so now we have our X value at equilibrium. So again, if you like to write it all out, that's fine. If you like to use your ICE table and write it in the ICE table, whatever worked for you last unit will work here as well, okay? I'm not sure I understand. Well, you didn't take chem. Okay, so this is technically, the way I've written it, we found the OH concentration, but the X value, it's always 1-to-1, right? So it's going to be the same. Again, scientific notation or not, that doesn't matter to me. Don't forget the concentration units. We can sub in X over here. And your textbook, again, uses the 100 rules so liberally. Even here, they might not even do this subtraction. But to me, why not? I don't know why they do that. They're very lazy chemists. Okay, so since we have a base, technically this is going to be Kb. So in a question like this, with lots of different things we're going to do, some people like to put boxes around their answers, even if you're not really a answer statement kind of person. And again, once you've done the ICE table, then use the formula sheet to help you. So now it says, so we found KB, great. Now it says to do KA. So KA times KB equals KW. I don't want to squish. Okay, so we just solved for KB, KW. Actually, let me write it the way. Okay, so the value for KW is given, the KA times KB equals KW is given. So once you do the ICE table, this should the formula sheet should definitely help you make sure you get every single answer that your question that you're asked for, okay? So now you just have to solve for KA by dividing by the KB. Okay, and the KA should be very, very small. Okay, times 10 to the negative 11, that is a small number. Again, maybe you would like to emphasize your answer. Okay, and then it wants us to do pH. So you have two options, just like that one example with the base we did for strong acids, strong bases. So pH is calculated negative log H plus, which we don't have. But you can do POH and then use pH plus pH plus POH equals 14 to find pH, which is the least amount of math. You could also do KW equals hydrogen ion concentration times hydroxide, solve for hydrogen, and then do pH, but that is a little bit more math. So usually students do not choose to do it that way, but you totally could. And all of those formulas are on the formula sheet, okay? Okay, so whether it's a strong acid or strong base or weak base, there is always going to be that extra step with the base. We don't deal with POH scale, so you're always going to have to change it into pH from the POH. Okay, so pOH, a pOH of 2.2, first it might be like, wait a minute, that doesn't make sense. Isn't low acidic? Yes, because we don't deal with pOH. Once you change it into pH, it's more above 7, which makes sense. It's a base. But again, you can do the same sort of logic. It's a weak base. It's not super close to 14, but it is definitely above 7. So this homework is much more intense than yesterday's for sure. And as like each problem, you could be asked sort of different things. So I don't recommend that you just do 556 number 3 and be like, okay, I did some homework, I'm done. Take a look at the different types of problems. Take a look at which ones are basic and don't just try the acidic ones, okay? This unit is very compact, so the review worksheet is not super extensive because I'm hoping that you'll do some of the homework to get yourself ready for the test as well, okay?